In the first part of the question, we have to determine the value of d upon dt q for the case q is equal to 1 using energy time uncertainty principle. Um, so, in quantum mechanics, wave function psi is a quantity that mathematically describes the wave characteristics of a particle. One commutates with everything, and this proves the conservation of normalization. Therefore, value of d upon dt psi is 0. Therefore, the value of d upon dt q for the case q equal to 1 using time um, energy time uncertainty certainty principle is 0. Now in the next section we have to determine the value of d upon dt q for the case q equal to h, again using the energy time uncertainty. So commutating anything with itself makes 0. So therefore d upon dt h becomes 0. This conserves the energy if h has no explicit time difference. Therefore, d upon dt q for the case q equal to h using the energy time uncertainty principle is also 0. Now, in the next section, we have to determine the value of ddt using for the case q equal to x. So, the time derivative of x is directly related to the expectation value of momentum and inversely related to the mass. That is, dx upon dt is equal to I upon reduced Planck's constant multiplied by Planck's constant hx. This is our equation 1. And it is known that the combination of uh, commutation of xh is equal to I h upon m. Thus the commutation relation for x h is equal to minus I h reduce Planck's constant upon m. So using this condition in equation 1, that is this one, we will get dx upon dt is equal to I h minus I h p upon m. So that is p upon m. Therefore, the value of d upon dt q for the case q equal to x is, now using the energy time uncertainty principle, is dx upon dt is equal to p upon m. Now in the last section we have to determine that d upon dt q for the case q equal to p using the uncertainty energy time uncertainty principle. So the commutation relation between HP is p square upon twice m plus p. So this equation can be written as p is equal to I reduce Planck's constant partial integration of b. This is our equation 2. So writing this equation for dx upon dx upon dt is I reduce Planck's constant I reduce Planck's partial uh, integration of b, that is equal to minus x. Therefore the value of d upon dt q for the case q equal to p using time energy time uncertainty principle is d upon dt p is equal to minus partial integration of v.